Yeah, thanks for having me. And thanks for putting me on first. I just got back from some travels in the United States, so I'm now in Singapore time zone. Normally, I'd be pretty awake by now, but I got COVID while I was traveling, and it's been just getting over the end of it. So I may crash out before the end of the session altogether, and I'll catch up on the notes. But anyways, I was asked to talk a bit about project I'm working on called Precursor, and specifically about the secure bootloader and self-provisioning aspects of it. And so first, I guess I'll just familiarize people a bit with what Precursor is. This is a picture of the device itself. It's basically a mobile device, a handheld device. You can put in your pocket, walk around with it. And you can do things that it's designed for things like communication, text communication, voice communication, authentication. So it has like a password vault application for right now. They can use to keep TOTPs and U2F, FIDO passwords, that sort of thing. And also, there seems to be a lot of enthusiasm about potentially turning it into a cryptocurrency wallet of some sort. But that's not our direct mission right now. We're currently focused on the communication applications. And the types of people we designed it for, our kind of threat model and the end users we think about are primarily at-risk users, so high-value targets, either politically or financially, people who may be under threat from APTs, and also, honestly, a lot of devs and enthusiasts, people who are really just excited about getting into secure technology is a big demographic for us. And we also put an emphasis on the device design itself from the bottom up to make it not just sort of English speaking only audience, but we want to be able to target sort of a global audience. So like on the piece of hardware you see there, that little keyboard overlay can be swapped out with an overlay that has different language glyphs on it, for example. Another question I wanted to kind of cover before we get into the nitty gritties is why are we? Hello? Yeah. Oh, okay. I think so. Another thing I want to get into is like, why are we doing a device and not just a chip? And from when we think about security, we don't think about just private keys being the only thing we're trying to protect. We actually want to protect overall your private matters, right? So the problem is that if you actually want to protect the end user secrets, you have to think about the screens and the keyboards being logged. And so, this boils down to the secure IO problem, where if you're on Android, for example, and you install an IME, this wonderful little pop-up will show that you just click through that says, oh, by the way, this thing can keep all your personal data like passwords and credit card numbers. Is that all right? And you just click OK, and you think, oh, what could possibly go wrong with this, right? I have the security enclave that I put all my private keys inside of, but I just consented to basically having a keyboard logger and all the data being funneled out. And it turns out this is just a wonderful backdoor that makes some regimes not care about end-to-end encryption at all, because some IMEs are very hard, and there's only a few of them that can handle certain languages, and so and that's perfectly fine for getting a hold of the data, despite the fact there's lots of encryption everywhere else. So that's why we think about it from the system level. We want to make sure that from the tips of your fingers onto the keyboard to the pixels hitting your eyes, the entire path is trusted, and that you have some confidence in that the data has the provenance of the data. So this is very quickly a system level diagram of the device. We sort of divide it into an untrusted domain and a trusted domain. That's the orange on the left is untrusted, the brown on the right is trusted. We throw stuff like the Wi-Fi chip and some power control stuff in the untrusted domain. A trusted domain, we put things like an FPGA, which is our soft core CPU that we use, the SRAM, audio codec, and the keyboard. These types of things that we want to keep within that trusted domain is all in there. Now, overall, we're using an FPGA system to help vet our use cases, develop our applications, test our IP blocks, hammer out kernel integration issues, and test things like our secure bootloader, for example. Eventually, we do want to get this sort of taped out into ASIC, although the fact that we're using an FPGA helps us get around one of the thorny issues in terms of supply chain, which is like, has someone tampered with your chips? By using an FPGA, we sort of sidestep that because we can basically say, hey, well, a user can go ahead and compile their own CPU with a random seed, and it makes it much harder to insert a backdoor inside of the supply chain at the CPU level. But eventually, for cost reasons, for reach reasons, for performance reasons, we're going to have to migrate to an ASIC, and that's a long-term process. But I'm very happy that we have basically a full system that we can run on an FPGA right now, that we can go ahead and just vet all the use cases, the kernel, and the apps. It's pretty handy as a dev platform to have such full coverage of the end application before we do an ASIC. So we think about security as a whole system, not as a component. So we also include the software supply chain in our threat modeling itself. We like to think about all the bits and pieces that go into building the hardware, in addition to building the firmware that runs on the hardware. So this is a slide from a talk that I put together called From Boot to Root in 1 hour. So this is basically the long version of the talk that I'm giving here, which I'm compressing to 15 minutes. Boot to Root in 1 hour goes through like basically everything from the reset vector itself. Actually, it goes all the way back to the SoC Verilog and the Python descriptions and LIDX and that sort of thing. Talks to the process of compiling it, the boot vectors, the secure bootloaders, the train of trust, all the way to basically the root keys that are provisioned on the device. So if you want to really take a deep dive, scan that QR code. All the URLs in here I've embedded as QR codes as well, in case someone wants to just split off and look at that, not listen to me blab on. But basically, you know, we try to track all of the pieces that we're putting into the software supply chain, and so that we know at least how big the attack surface is. You know, honestly, realistically, these tools are so complicated that I can't say that, you know, with any confidence that, you know, we know there are no backdoors in any given one of these tools, but at least we've enumerated the tools and the problems that we can have with them. We're, you know, in particular, for example, when we think about the firmware side, when we write our Rust code, we try hard to not pull in lots and lots of third-party libraries. We'll actually vendor in things and pair out libraries that are too bloated to make sure that our supply chain, our software supply chain attack surface is minimal. And then that all, of course, compiles down into the FPGA stuff, which we'll get into just shortly. So yeah, like I said, we only have a few minutes, so let's get on to the SoC. So the actual SoC that we use, this is all compiled in FPGA, consists of a RISC-32 iMac soft-core CPU that's all done in LIDX. And there's a whole gob of peripherals on the lower left-hand side. They're connected by the CSR I/O over here. Is this thing? No. Okay, this cursor does not give me a nice little laser pointer or anything like that, right? Nope. And then on the right-hand side, we have some memory mapped I/O. On the top right, we have the cryptography complex, which has all of our crypto hardware primitives in it. This diagram's a little bit dated, but it's basically correct. From the standpoint of doing secure boot, these are the areas we actually want to look at. So there's the CPU, of course, is important. We have some on-chip RAM, some on-chip ROM. And then we have a key ROM on the inside. The size of that is actually dictated by the size of the LUTs of the FPGA. We actually don't use all of the bits that are in it right now. We have a Curve 25519 engine in hardware and a SHA-512 engine in hardware. And so those are secure boot relevant items. And in terms of the artifacts that are involved in boot, this is sort of the gross layout of where everything is. So the actual source code, I mean, everything in this project is open source. Everything I talk about is published online. So I've included the QR codes for URLs that will drop you directly into the bootloader signature check code and the kernel signature check code. So if you just want to like not listen to me talk and just read the code, go for it, right? But basically, the life cycle of the secrets, they start with the sort of inside the spinal ROM. So the lower half here is the actual spinal ROM itself that contains all the code at rest. The bit stream is encrypted with an AES-256 key, decrypted by the FPGA hardware. loaded in, creates a soft core. Inside the soft core contains a boot ROM itself, which has a set of public keys on the inside. And it'll go ahead and it will sort of do a signature check on the next level loader. And the reason why we have to have a next level loader is that we want to keep that loader inside the FPGA as tiny as possible. We only have 30 kilobytes of space. So all the features we need to properly load the kernel is not going to fit in that. So this is a very minimal, just a signature check, shim, and run thing. The loader itself then goes ahead and inspects the kernel, sets up the page tables, blah, 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 sort of stuff, pulls in the kernel. And then the kernel, after it's loaded, will finally turn itself back around again and check to make sure that both the gateware itself has not been modified and that the loader itself has the correct attributes to it. So the whole thing sort of seals itself in a circle at the end of the day. So a little bit more about the actual code itself. So the whole bootloader itself is written in pure Rust, except for a tiny assembly stub. The assembly stub is so small, I can just show it to you right here. You can look at it. It's basically a canary pattern. Fill the stack, clear the cache, set where the stack pointers are going to be, and then jump to Rust, right? It's pretty much as small as you can get in terms of an assembly stub, so there's nothing too ugly going on there. And then the chain of trust starts there. The loader itself is, like I said, we try to keep it very minimal. So we check the ed25519 signature against a set of known public keys of the loader itself. The bootloader has some very rudimentary graphics on the inside of it, so it can drive the LCD and put some character graphics up so the users know if the signature check fails, it'll print a message or something like that, or whatnot. And it has some countermeasures on the inside so that if the signature check does fail, it fuses out the ROM, makes it inaccessible. Someone's basically trying to attack it, trying to harass people trying to get secrets out that way. And then that jumps to the loader itself, which then again takes another set of public keys. And very importantly at this point here, I'm kind of at this middle box here where I'm talking about the loader and reading down this list. We handle all the suspend and resume things that might happen before we go into the kernel. It turns out suspend and resume is like a real big freaking pain in the ass to deal with in almost any sort of OS, because essentially when you're resuming, it breaks a lot of, you can break a lot of security assumptions there. You're taking a machine that basically shut all the way down and then bring it back up again in sort of wedging a lot of values in different registers. And so actually when it was really nice to be able to have an FPGA based system. So, when we had sort of abstraction breaking issues in terms of the resume, we were able to sort of fix them in hardware and not have to put horrible, awful bodges inside of the OS to deal with that. Anyways, if it turns out that resume, the resume process is pretty quick, just short circuits and resumes where we left off. Otherwise, we clear the full RAM to make sure that none of the previous session secrets are there. And then there's this long sequence of things where we basically set up, text, data, BSS sections, create virtual memory pages, map in all the threads, and then start running the actual OS itself. So that's basically the chain of trust and the whole thing that it goes through. And these two code files will basically walk you right through it. They're not too big. So then I'm going to talk a little bit about the key ROM layout, but in order to make sense of that, I need to talk a bit about the threat model that we have to make sense of it. So most ASIC secure boots are designed with the assumption that you don't trust the user. And there's ultimate trust in the manufacturer and supply chain. And their goal is to enforce manufacturer service provided policies upon the user. So you want to, enforce some sort of DRM or a usage case or force an update or something like this. And oftentimes the aim is to prevent users from running arbitrary code on their devices. We have a really different threat model. We don't trust the manufacturer. You shouldn't trust me. Don't trust any manufacturer. We don't trust the supply chain. We don't trust our supply chain or anyone else's supply chain. And so, our goal is to empower users to control and protect their own hardware. And we want to just, as much as possible, complicate sort of tampering of the hardware and also prevent remote exploit persistence. So if someone's able to sort of actually get a foothold in the device, prevent someone from putting some permanent code inside the code at rest that can be loaded on the next boot without the user knowing. And so to that extent, the key-ROM layout basically consists of the most highest privileged key is a self-signing key, which actually the users themselves don't even know. It's actually generated entirely within the device itself, and that is used to protect the code at rest on the device. Normally, if you're going a typical ASIC route, this would be like a factory burn private key that only the factory would know and the users have no access to. We also provide a developer public key, which is a kind of well-known public key. This is what we use right now to publish updates. Anyone could sign with it. The purpose of it is more basically just to, integrity check that, data wasn't accidentally corrupted on the fly, but it's not going to do anything against an adversary because anyone could sign with that key. And then there's currently also a third-party public key that's provisioned but not used, where if someone wanted to do a certificate authority and publish code and say, here is a code base that you can trust and use and get data from, people can go ahead and opt to trust that particular certificate authority to sign the code. Let's see, the size of this ROM is oversized for what it is. That's because the Spartan 7 ROMs are so big. It didn't make sense to make any smaller. We do some anti-rollback. So there's a global anti-rollback that's implemented, because we're using a lot, and we don't have single E fuses, but we can basically code an 8-bit word. We can have up to 255 rollback stakes, and that's done by actually every single one of the keys. We hash them repeatedly. As basically on the first boot, we will hash them 255 times, and then every single time we want an anti-rollback, we'll go ahead and increment that count and hash it one less time. And this gives you the property such that if we set the rollback bit, anyone who is authorized to run at that particular rollback level can go ahead and hash their current key one more time and decrypt an old image. But you can't predict what the next image would be because that's essentially tantamount to reversing the hash. And another thing I just want to note is that the private keys themselves are also protected by a password. So even if you were to be able to dump the entire key ROM, you couldn't actually sign a code image without the user also providing the other factor as well. So it's another layer of protection that we have, acknowledging the fact that keys are oftentimes dumped and extracted. So the whole documentation for this and discussion of it is also available at the QR code in the lower right and the URL that's been placed up there. So we wrote everything for bootloaders in Rust. A bit on the pros and cons of why we did it and our experience doing it. So the pros is, you've probably heard this, Rust is a memory safe language, it's strongly typed. It's got pretty good community support for cryptography via the cryptography.rs guys. The cons of it is that you do get a larger binary size than if you're doing C or hand rolled assembly. And in particular, if you're targeting an ASIC, every square millimeter counts. We were only able to get our bootloader down to 32 kilobytes, and all we're sticking in there is like hardware initialization and drivers for the ED 25519. We don't actually have the ED 25519 crypto code in there. If we put that in there, the bootloader would grow to like 128K. So we had to use hardware crypto blocks to keep that binary size down to a minimum. We also have some character graphics and some minimal key management in there. There's a pretty steep learning curve on Rust. I wrote a kind of a blog post. You can read all about my opinions about that. Also, that QR code, if you scan it, it'll drop you into the thing that sort of talks about some of the deeper pros and cons of using Rust and some of the challenges I've had learning it. So then finally, I want to touch a bit on the self-provisioning side of things. So self-provisioning is, setting up your keys on the device itself. So step one is get a good TRNG. So if you don't have a good TRNG, everything's lost. Like, just don't even start. Don't even wait. Don't go past go. Don't get $200. Redesign your whole thing. So we actually have two TRNGs in our system. We have an avalanche generator, which is an external discrete solution. And that's because we don't necessarily not necessarily trust what's on the chip. And that has an independent hardware monitor of its own. to monitor its health. And then there's a ring oscillator that's inside the chip itself. And that's because an external discrete TRNG is pretty easy to tamper with, from a like evil maid style attack or something like this. And so hopefully by combining those two together, we kind of get the best of both worlds, and any flaws in one is compensated for by the other. The avalanche generator, of course, requires an ADC, which is a bit expensive from a BOM cost standpoint, but it's free on an FPGA, so might as well. And those get XORed together, thrown into FIFO, put through a ChaCha-8 CSPRNG to go ahead and condition the data. The ChaCha-8 is not necessary for good performance. It's there because I like belt and suspenders. We characterize all the avalanche generators before it goes into CSPRNG for quality, and it passes all of the sort of FIPS tests there. But we add that anyways because I'm still very paranoid about something, some dropouts and whatnot. And then that drops into a pair of FIFOs. We actually have a port dedicated just to the kernel itself for TRNGs, because the kernel very importantly needs TRNGs early on. And then there's a user port where all the servers share the TRNG data as well. If you want to read more about the design and architecture of the TRNGs and learn about various aspects and also some other experience we did with like modular noise generation, the URL and QR code there will drop you to a post that I put up documenting all the deliberations there. So then step 2 is generate your keys. If you pick the right cipher, this is easy. So if you're doing something like RSA, it's hard. Like, you have to like find primes and there's, weak keys and all that sort of stuff. We're using Curve 25519 in AES. So basically there are no weak keys. You basically just get a good quality random number and you have your keys at that point in time, and then you save the keys. And so this is very specific to an FPGA, this next few steps, but I'll talk about it anyways because I think it's pretty interesting. So when our device boots, it comes out of the compiler with nothing in the key-ROM box. It's basically empty. Actually, it's a bunch of random junk, but it's not actually the data you're going to use. The FPGA itself has no key. It's the 0 key. It's the AS key that's all 0, and the crypto engine has no keys. So that's the state that things start in. We self-provision keys and basically put them into where they would be located inside of the crypto ROM itself, inside the soft SoC itself. But the problem is, of course, is that next time we reload the SoC, we're going to get that old image that doesn't have the keys on the inside. So then what we do is actually we reverse engineered the bit stream format for the FPGA. We decrypt the FPGA on the fly because we have a copy. It's a 0 key initially. We go ahead and we patch in our new keys into the bit stream, and then we write them back out into the right position in the bit stream and re-encrypt them to the new key that is used to actually encrypt the overall bit stream itself. So it's a kind of an interesting bootstrapping process. And so at the end of the day, we can go ahead and actually finally blow the hardware encryption key on the device itself, and do it in a way that, for example, you can't do readback, AS only boot, so on and so forth. And so at that point in time, the device would be fully sealed, in theory, barring hardware problems in the FPGA, which of course there are hardware problems in the FPGA allow sort of Oracle attacks with AES. But if that didn't exist, it would be a pretty good solution in terms of being able to lock away the data after self-provisioning. But that's sort of the whole loop that we do there. So that's basically secure boot and self-provisioning in a nutshell. Kind of went through it as blazingly fast as I could. I think I hit the time goal. If you want more information about the hardware, the QR code on the left will take you to precursor.dev. It has more information about the hardware. The devices themselves are actually currently for sale. They're available. They're in stock. You can go ahead and get them and dev on them and play with them if you want to. If you want to go ahead and actually ask me more questions later on, or if you have just general, or you just want to just follow along with all the development work, we have a matrix room, which is the QR code on the right-hand side. You can scan that and you can join the room. And I I try to be responsive there and try to respond to everything within a reasonable amount of time when I'm not on vacation. And so with that, I guess we can open to some limited Q&A